Welcome to video 19.1b, the last video of topic 9 and 19. We will continue our study of electrolytic cells. In terms of accessing your prior knowledge, it will be helpful to remember electrolytic cells from 9.2b, specifically that there is a power supply for an electrolytic cell that pushes electrons towards the cathode so that the cathode has a negative charge. Cations are attracted to that cathode, and this is where reduction takes place. So, red cat still works. The reduction happens at the cathode. An ox still works, as the anode is where oxidation takes place. So it'll be helpful for you to remember this. The electrolyte in 9.2b was actually a liquid or molten salt. In our work today, we're going to be looking at aqueous solutions. It will help us to remember the dissociation of ions when an ionic compound dissolves in water. So the metal ions and the non-metal ions. So magnesium nitrate, as an example, is Mg2+ aqueous ions, and 2 moles of nitrate ions for every 1 mole of magnesium ions. Just remembering that will be helpful. The big idea is the same as 9.2b for electrolytic cells. Energy conversions between electrical and chemical energy lie at the core of electrochemical cells. Of course, we are focusing on electrolytic cells in this particular video. A series of syllabus statements that we will work through. In terms of electrolysis of aqueous solutions, if we have some general electrolyte, some metal, some non-metal, at the cathode, water can be reduced to hydrogen, or the metal ion can be reduced. At the anode, water can be oxidized to oxygen, or the A- ion can be oxidized. So we're going to have to make some choices in this video. The discharge of an ion at the electrode in these cases is known as selective discharge. Selective because we have to actually give some thought to which ion will be discharged. The outcome is determined by the following factors. Number one, the relative standard electrode potential values for the ions involved, which we'll learn about. The relative concentrations, which we'll learn about. And the nature of the electrode, which will also play into our discussion. 4-step process. We will focus mostly on step 2, where if there is more than one possible reaction at the electrode, we have to figure out which reaction will be taking place. So let's look at the electrolysis of water with sodium hydroxide. So number one, let's look at the ions that are present. Since sodium hydroxide will dissolve to form sodium ions and hydroxide ions, the sodium ions will be attracted to the cathode and the hydroxide ions will be attracted to the anode. At the cathode, possible reactions. So possible reactions at the cathode, we have the sodium ions being reduced to form sodium metal, or we have the hydrogen in water being reduced to form hydrogen gas. Okay, let's look at these values for the standard electrode potential. So water is preferentially reduced and hydrogen is produced. Hydrogen is produced at the cathode. This is the more positive value, or well, actually if we look at it in this case, it is the less negative value. So the sodium ions will not get reduced, which makes sense because as soon as the sodium metal were produced, if it were to be produced, it would react with water to form sodium ions anyway, and so that's just not going to happen. This more positive value, less negative value, is the preferred reaction, and so water will be reduced, the hydrogen in water will be reduced to form hydrogen gas. At the anode, So two possible reactions. I have hydroxide ions forming oxygen gas. So the oxygen and hydroxide being oxidized. The hydroxide is going to come from the sodium hydroxide or water. The oxygen and the hydrogen in water, specifically the oxygen, can be oxidized to form oxygen gas. So these reactions have been written in the reverse of the data booklet. So these are written as oxidation reactions. Since they're written as oxidation reactions, the more positive value or less negative value will be the preferred reaction. So that means that this is our preferred reaction, because this is a more positive value or less negative value. So the hydroxide ions are preferentially oxidized and O2 gas is discharged. So I have the two half reactions that would be favored selectively at each of the two electrodes. If I add those together, this is 2 electrons, this is 4 electrons, so I need to multiply this reaction by 2. And when I do so, I end up adding those together. I get 2 waters makes 2H2 plus O2 gas. I want you to notice the 2-to-1 ratio of hydrogen to oxygen. That's important. So what would we observe? Well, a colorless gas would be evolved at both the anode and the cathode. The ratio of volumes of the gases would be 2-to-1, if we remember Avogadro's law from topic 1. And the pH at the anode will decrease as H plus is released, and the pH at the cathode will increase because OH minus is released. So I will have different pHs depending on where I'm at, the anode or the cathode. Let's look at what if I had dilute sodium chloride. I would have sodium ions present and I would have chloride ions present. We already know that the sodium is not preferentially reduced, so I'm going to produce hydrogen gas at the cathode. In terms of possible reactions at the anode, water can be oxidized to form oxygen gas, or chloride ions can be oxidized to form chlorine gas. Based on the values, the values favor the oxidation of water. However, it's a bit more complicated. When the concentration of chloride is low, water is oxidized. So this is favored at low concentration of chloride. And this reaction is favored at high concentrations of chloride. So we can actually produce chlorine gas by using a relatively high concentration of chloride. It says here if it's greater than about 25% by mass. I'm sure you could figure out what the molarity of that would be. Typically greater than 1 molar. If we have dilute chloride or versus concentrated chloride. On IB exams, I have seen them refer to this as dilute and this is concentrated, just to kind of use words to describe those two. I wouldn't get so focused on what's the number that separates concentrated from dilute. Don't focus on finding that one exact number. Focus on the big picture. So the overall balance equation when chloride is discharged, 2 electrons here, 2 electrons here. So I have sodium chloride and water producing hydrogen gas and chlorine gas and sodium hydroxide. Okay. In terms of observed changes, gases evolved at both the anode and the cathode, hydrogen and chloride. Chloride is identified at the anode through strong smell and bleaching effect on damp blue litmus paper. We probably don't want to be smelling the chlorine gas, I'm just going to tell you. An increase in pH of the electrolyte will occur due to the release of the hydroxide. Copper sulfate is another one that we can use for electrolysis, and it will be dependent on the electrodes used. Most common electrodes are carbon, which in this case graphite or some other inert electrode, or copper, and we'll learn about both of those scenarios. With an inert electrode such as graphite, the ions present are copper ions and sulfate ions. So at the cathode, copper can be reduced, or water can be reduced to form hydrogen gas. Which of those two will be favored? Copper will be preferentially reduced because this is the more positive value. Okay? More positive value is the reaction that is favored. At the anode, water is preferentially oxidized. If you find sulfate ions on your data booklet, it will simply not be in the form that will matter. The sulfate ions simply aren't oxidized easily. So the overall balance equation, I have this reaction happening and I have this reaction happening. So copper sulfate and water are going to form copper solid, oxygen gas, some H plus, and some sulfate ions. So this is essentially sulfuric acid, which means there would be a decrease in pH since I'm producing an acid. What we would observe, a pinky, I like this word pinky brown color of copper deposited on the cathode. Brown, I've never really seen it be pink, I've seen it be more brownish black. Colorless gas evolved at the anode, that would be oxygen. Decrease in pH of the solution due to the release of H plus ions. And the loss of intensity of the blue color due to a discharge of copper ions. The copper ions are being reduced to form copper solid. These are ions that are aqueous, that have a blue color. This is a solid that no longer is dissolved in water, and therefore the blue color should decrease. What if I had a copper electrode? The same ions are present, copper ions and sulfate ions. Copper is still preferentially reduced at the cathode. At the anode, copper will be preferentially oxidized, supplying electrons for the reaction dissolving as copper ions. This one is a bit odd. So the overall balance equation is, well, I have this reaction and this reaction. Copper cancels, copper ions cancel, the electrons cancel. I don't really have an actual overall reaction taking place. I have two half reactions that have a net effect of no difference. But what's happening? Well, then what really is happening is the movement of copper ions from where it is produced at the anode to the cathode where it is discharged as copper sulfate. So the anode will reduce in mass and the cathode will gain mass. That's something to keep in mind. Here's a diagram which I think is helpful for this particular scenario because it does seem a bit odd at first. Pinky brown color of copper deposited on the cathode. This cathode would end up having this pinky brown color of copper deposited. It would actually be deposited down here in this part of the electrode where it's in contact with the water. Disintegration of the copper electrode. This electrode is going to disintegrate and get smaller. It is sometimes used where this is an impure anode and this copper over here would be pure copper. This is a way of purifying copper. No change in pH in the solution because there are no hydrogen ions or hydroxide ions being created or used up. And no change in the intensity of the blue color because we are forming copper ions and we are removing copper ions. So there's no net change in the color of the copper solution. Here are some syllabus statements related to some calculations. So if I want to quantify charge equals current times time. So if I want to figure out like how much copper is going to be deposited, charge of Q is measured in coulombs. That depends on the current. I is measured in amps and T is measured in time, in seconds. The charge carried by 1 mole of electrons is known as a Faraday. It's 96,500 coulombs. So in this scenario, if I know the current and I know the time, I can figure out the charge, so like the total number of electrons that have been transferred. If I know the charge and I divide by Faraday's constant, I can figure out the number of moles of electrons. And if I know the number of moles of electrons, so this is essentially the charge per mole. If I know the number of moles of electrons, I can figure out how many moles of product would be produced. And from that, I can figure out the mass of the product. So let's try it. How many grams of copper are deposited on the cathode of an electrolytic cell containing copper chloride if a current of 2 amps is run for 15 minutes? And then we'll come back to question B. First, we calculate the charge, then the moles of electrons. So charge equals current times time. Time needs to be in seconds. So I have the amperage, which is the current, times the time in seconds. I get 1,800 coulombs. 1,800 coulombs divided by 96,500 coulombs per mole tells me that I had 0.01865 moles of electrons. It's not very many electrons, actually, if you think about a mole. So now I need to use the mole ratio and the electrode half equation to determine the moles of product. The electrode half equation I'm speaking of here is the reduction which is taking place at the cathode. There are 2 moles of electrons required for every 1 mole of copper. So 0.01865 moles of electrons, it's 2 moles for every 1 mole. So I have to take that number divided by 2, 0.01865 moles divided by 2. And I get 0.00933 moles of copper, which I can convert into grams. So I get 0.593 grams of copper. Not very much, actually. Question B, how would the amount differ if the same conditions were applied using CuCl instead? Here, copper is not 2 plus, but copper is 1 plus. Since copper is 1 plus, it only takes 1 mole of electrons to create 1 mole of copper solid. So I actually have twice as much copper here. So I have 1.19 grams. So the number of electrons matters in terms of the moles of product produced, which obviously then determines the grams of product produced. Here's a comparison of sodium and lead. Sodium only requires 1 mole of electrons, whereas lead requires 2. So if I have the same current, I would have twice as much sodium by moles. Factors that affect the amount of product formed: the current, more moles. The duration of electrolysis, longer duration, more moles. The charge on the ion, smaller charge, more moles, because it takes less electrons to make the reduction happen. Last thing we're going to talk about is electroplating, which relates to the example we just looked at. And I'm going to demonstrate electroplating in class for you, if I can get the demo to work. Electroplating is often done for copper and sometimes some other elements, and it's used to coat an object with a metal. The cathode made of the object to be plated, and so the cathode is whatever we want to plate. What do we want to coat with copper if we're talking about copper electroplating? So if I want to electroplate a fork, the fork needs to be connected to the cathode and an impure silver, and this is plating it with silver, not copper. So I have a silver salt like silver cyanide. And at the anode, I have silver solid forming silver ions. And at the cathode, I have silver ions being reduced to form silver solid, and it will plate the fork in silver. We could do the same thing with copper. Copper anode, whatever object I want to plate in copper here, and so these ions will form in aqueous solution. The aqueous ions will plate the electrode. Connections to other topics. Whoa, that means you made it. Whew, that was a long video. Thanks for paying attention. Lots of connections to other processes, other topics. Here's a summary for you. First of all, electrode potentials and concentrations can be used to determine the products of electrolysis. Current, length of time, and identity because of charge of the ion involved determines the amount of products formed in electrolysis. And electroplating is a useful application of electrolysis. What else would you like to add to your summary? Checkpoint question. All right, read the question, take a look, pause the video, come back when you are ready. And the answer is C, 1 and 2 only. Metallic tin can be produced by the electrolysis of a molten salt containing Sn2+ ions, which change would double the amount of tin produced. Well, if I double the current, double the amount of tin. Double the time, double the amount of tin. But if I use 4+ ions instead of 2+, I will get half the amount, not double. Which means it is 1 and 2 only. So if you want some explanation, let's look at Sn2+ plus 2 electrons makes Sn. Sn4+ plus 4 electrons makes Sn. These are aqueous and this is solid on the right hand side. So if it requires 4 electrons, it requires twice as many electrons. For the same number of electrons, I'm only going to get half the moles of tin using this reaction as I am with this reaction. So using Sn4+ would not be helpful. Thank you for listening. I do appreciate your time. And I'm hopeful, ever so hopeful. Like the hope of all, the greatest of all hopes, that you will fill out my Google form. If nothing else, put your answer to the checkpoint question there. Please, I beg of you. Thank you very much. Have a great day. I'll see you in class.